See, D block elements in the modern periodic table start from 4th period. Start from 4th period. Generally, D block elements means they are actually 3D series. Generally, you feel that 3D series means they may be starting from 3rd period. They are not actually starting from 3rd period. They are starting from 4th period. D block element start from 4th period in the modern periodic table. Simply, I will introduce what are D block elements, what are D block elements, what are transition elements, what are transition elements, and what are typical transition elements. What are typical transition elements? Typical transition elements. Now, D block elements. In the modern periodic table, the elements are classified according to entry of differentiating electrons. Entry of differentiating electrons. Differentiating electrons. Entry of differentiating electron. What is differentiating electron? You can also consider the last electron. Differentiating electron or the last electron you can consider. Now, to explain this particular differentiating electron, let me show calcium electronic configuration. One more thing. In the modern periodic table, each period you take it as what? A shell. Now, you are talking about these D block elements starting from 4th period, I said. Therefore, let me write 4 shells. 4 shells. Therefore, first shell, second shell, third shell, and 4th shell. So, after calcium, you are getting this particular D block elements, scandium 21 to zinc 30. Let me show first the electronic configuration of calcium. See, I am writing on the board calcium electronic configuration. Now, let me write like this. Now, 1s2, 2s2, 2p6, 3s2, 3p6. This is the electronic configuration of calcium. Electronic configuration of calcium. Now, let us talk about scandium 21 to zinc 30. Scandium 21 to zinc 30. These are all the electrons. Let us consider as differentiating electron. What is differentiating electron? The atom which is carrying 20 electrons is calcium. The atom which is carrying 21 electrons is what? Scandium. Therefore, the differentiating electron between calcium and scandium is what? 21st electron. Now, you talk about titanium. Scandium to titanium, the differentiating electron is what? 22nd electron. That is, the next higher electron is the differentiating electron. Let me show where this particular 21st electron is actually entering. Look at here, this particular 21st electron is not entering into the valence shell. Not entering into the valence shell. But it enters into the d orbitals of the penultimate shell. The electronic configuration of scandium is what? D1, 3D1. It is not entered into the valence shell, but entered into what? Penultimate shell d orbital. Therefore, the elements in which the differentiating electrons enter into d orbitals of the penultimate shell are known as D block elements. Next, let me introduce what is this particular transition element. The element which are carrying incompletely filled n-1 d orbitals. n-1 d orbital, let me say d1 to d9, either in their atomic state, or in their chemically significant oxidation states. Chemically significant oxidation state. The element which are carrying incompletely filled n-1 d orbital in their atomic state or in their chemically significant oxidation states, we call them as what? Transition. In a single word, transition means which are carrying incompletely filled d orbital. Incompletely filled d orbitals are known as what? Transition elements. Next, typical transition elements. Typical transition element. Let me show you, explain this. Let us consider first B group and again second B group of elements. Recollect yourself what are first B group and second B group. First B group of elements are copper group of elements, and second B group of elements are zinc group of elements. Copper group means, you know, copper, Ag and Au. Copper, Ag and Au. Zinc group means well known to you. This is what? Zinc, cadmium and Hg. Zinc, cadmium and Hg. Now you consider this particular copper zinc, Ag cadmium, Au, Hg. This is nothing but 3D series. This is 4D series, 3D series, and again this is what 4D series of elements, and this is what 5D series of elements. In addition to this particular first B group, second B group, let me write in the case of 4D one more element I am writing, palladium. Palladium. Now let me show the electronic configuration of these particular elements. The 7 elements are written on the board. 7 elements are written on the board. Now this particular electronic configuration of this particular copper is what? N-1 D10, it is what? NS1. This particular zinc is N-1 D10, it is what? NS2. Come to this particular palladium, the configuration, remember 4D10, it is what? 5s0. 4D10, 5s0. 5s0. Now what do you understand by this? Looking this 7 element, observe these 7 elements are carrying fully filled d orbital. Fully filled d orbital in their atomic state. Therefore, in their atomic state, they are not considered as what? Transition element. In their atomic state, these are not considered as transition element. But to consider copper, Ag and palladium, copper, Ag, Au and palladium in their significant oxidation states. In their significant oxidation state, consider copper plus 2, consider Ag plus 2, consider this particular Au plus 3, consider one more palladium plus 2. In their significant oxidation states, look at here, they are gaining D9 electronic configuration, D9 electronic configuration, D8 electronic configuration, D8 electronic configuration. What do you understand by this? In their significant oxidation states, all the 4 elements gaining incompletely filled d orbital. Then they are following this transition behavior. Transition behavior. Basically what I said, fulfilled d orbitals, they are not transition. But in their significant oxidation states, they are gaining incompletely filled d orbital. They exhibit transition. Basically they are not transition, but now and then they are exhibiting transition. They are representing the transition behavior. Therefore, these are not what? Typical transition elements. Come to the next point, what are non-typical transition elements? In the case of zinc, cadmium and Hg, zinc, cadmium and Hg, in their significant oxidation states, consider zinc, cadmium and Hg. In their significant oxidate, look at here, zinc, cadmium and Hg, second B group of elements, their common oxidation state is plus 2. In their plus 2 oxidation state, still they are carrying only D10. In their atomic state, look here, D10. In their significant oxidation state also, D10. When they are carrying D10 electronic configuration, they are not exhibiting any transition behavior, either in their atomic state or in their significant oxidation state. Therefore, zinc, cadmium and Hg are not considered as what? Typical transition. Copper, Ag, Au, palladium are typical transition element. Zinc, cadmium and Hg are non-typical transition elements. So these are the definitions of D block elements, transition elements and typical transition element. Let me show what is the relationship between D block and transition. D block and transition. Relationship between D block and transition element. D block and transition elements. D block and transition elements. Now, if you consider in the case of scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, let me see. You know the atomic numbers, this is what 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now, the electronic configuration of these particular, see, scandium is what? D1, D2, D3. This is exception, you know well. Chromium is D5S1, D5S1. This is D5S2. This is D6S2. This is D7S2. This is D8S2. This you know well again D10S1, and this is also what? D10S2. D10S2. What you are observing? Scandium 21 to nickel 28. Scandium 21 to nickel 28. They are all carrying incompletely filled d orbital. therefore they are transition elements. Next, scandium 21 to nickel 28. The differentiating electrons also enter into d orbitals of the penultimate shell. They are carrying incomplete filled d orbitals, transition elements. They are entering, the differentiating electrons are entering into d orbital of the penultimate shell, therefore they are d block. They are satisfying both the definitions. Therefore, this particular scandium 21 to nickel 28, we can consider them as what? D block elements and also as transition element. Therefore, all the transition elements are D block elements. All the transition elements are D block elements. Come to the next point. In the case of copper and zinc, you see copper and zinc. These are carrying the 29th electron and 30th electron. These two differentiating electrons entering into d orbital of the penultimate shell. They are d block. But they are carrying what? Fully filled d orbital. Look at here. They are carrying what? Fully filled d orbital. When they carry fully filled d orbital, they are not a transition. They are only d block, but not a transition. Therefore, this particular copper and zinc are only d block, but not transition. Therefore, let me say a statement here. All the transition elements are d block elements, but all the d block elements are not a transition element. It's a very, very important point to remember. All the transition elements are d block elements, but all the d block elements are not a transition elements. So, these are all the definition: d block, transition, typical transition, non-typical transition, and the relation between d block and the transition elements. Electronic configurations and group wise study. Group wise study. Group wise study. Look at here. All the S and P block of elements are classified as what? A subgroups. First A group, second A group, next third, fourth, fifth, sixth, seventh, and 0 group. They are all what? S and P block of elements are classified as what? A subgroups. First A to 7th A. But all the D block of elements are classified. All the D block of elements are classified as what? B subgroup. All the D block of elements are classified as what? B subgroups. B subgroups. Now, let me say here, in the case of scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Copper and zinc. Let me say it is 3D series. Next 4D series. Let us consider here. Here it is what? Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. Silver and cadmium. Next, let me say 5D series of elements. 5D series of elements. Now, here it is what? Lanthanum, hafnium. In between these two, well known to you, cerium to lutetium. This is what you call lanthanides. Next, lanthanum, hafnium. Then it is what? Tantalum, tungsten, rhenium, osmium, iridium, platinum, Au and Hg. Au and Hg. These are what? 3D series, 4D series and 5D series of elements. The numbering of this particular group numbers, let me give first. Copper group of elements, what to say it is what? First B, and zinc is what? Second B. First B and second B. This is what again? This is what? Third B and fourth B. It is what? Fifth B and sixth B. Sixth B and it is seventh B. Seventh B, and these particular 3 vertical columns kept under single group, what to call 8th group of elements. 8th group of elements. So, first B to what? 7th B and 8th group of elements. Let us discuss the group wise study of these particular elements. Let me talk about first B group. First B group. The first B group of elements resemble with first A group. First B group of elements resembling with what? First A group, because their common oxidation number is what? +1. First A group also +1. Therefore, these elements are exhibiting similarities with the first A group of elements. Next, one more thing, copper AgAu. Copper Ag, Au, generally known as what? Currency metals or what? Coinage metals. These are known as what? Currency metals, or you consider as coinage metals. Currency metals or coinage metals. These three metals are much more liked by ladies. Therefore, these particular three elements also commonly known as ladies metals. These are also known as what? Ladies metal. Currency metals, coinage metals, and ladies metals. Coming to second B group of elements. The second B group of elements exhibiting similarities with the second A group of elements, alkaline earth metal. Second A group of elements. Why? Their common oxidation number is +2. Second A group also +2. Therefore, this second B group of elements are exhibiting similarities with the second A group of elements. Come to the next third B group. Third B group. Now, this particular third B group is carrying maximum number of elements in the periodic table. This third B group is carrying a total of 32 elements. 32 elements. Now, here see this particular first, second, third, then you can take 6D elements also. After lanthanum, you can take it what? Actinium, you can write it what? Rutherfordium. In between these, you know, thorium to what? Lawrencium. Thorium to lawrencium. Now, 4 D block of elements, look at here, 1, 2, 3 and 4. 4 D block we can take. Next, these 14 lanthanides and 14 actinides both are coming under same third B group only. 14 lanthanides you take and again 14 actinides. Total how many elements? 32 elements. Remember, this particular third B group is carrying maximum number of elements in the periodic table, that is overall 32 elements. 4 D block and 14 lanthanides, 14 actinides, all are coming under third B group. Moreover, this particular third B group resembling properties with the third A group of elements, boron family, third A group of elements. Next, coming to fourth B group. Now, in the case of fourth B group, titanium is commonly known as what? Wonder metal. Commonly known as wonder metal. Why it is known as wonder metal? Because it is having some unique properties. What unique properties? It is actually its melting point is reasonably very high, and it is very hardest metal. Next, its corrosion resistance power is even more than stainless steel. Why? High melting point. Next, high hardness. Next, its corrosion resistance power is more than stainless steel. Because of some unique properties in the periodic table, this particular titanium is commonly known as what? Wonder metal. Wonder metal. Next, come to fifth B. Fifth B, nothing is there to discuss much. Leave aside. Coming to sixth B. Look at here, this particular tungsten. This particular tungsten is having highest melting point. This tungsten is having highest melting point among all the metals in the periodic table. Its melting point is around 3400 degrees centigrade. You can understand how much it is big. So, among all the metals, the metal with highest melting point is tungsten. Can you say lowest melting point? Among all the metals, lowest melting point is observed for mercury. Lowest melting point observed for mercury. It is minus 29 degrees centigrade. This is among the metals, highest is tungsten and lowest is what? Mercury. But among all the 112 elements you take, 112 elements, among all the elements in the periodic table, which is having highest melting point, you can say that carbon. Among all the 112 elements, now the carbon is having what? Highest melting point, that to be in diamond. In diamond, carbon is having highest melting point. Among the metals, highest is tungsten, lowest is mercury. Among all the 112 elements, the highest melting point observed for what? Carbon, that to be only in diamond. Next, coming to the next point. Come to 7th B group of elements. In this particular 7th B, this particular technetium is, remember, first man-made element. Technetium is the first man-made element. Among all the elements till now, many synthetic elements are there, man-made elements are there. First most synthetic element is this particular technetium. Look at here, this technetium is not naturally available. This technetium is not naturally available. Its non-availability in the earth crust we can explain based on Matach's rule. The non-availability of technetium we can explain based on Matach's rule. can explain based on Matas rule. I will explain later on what is Matas rule. In this particular group, consider manganese. Manganese in the finely powdered state. Take manganese, make into fine powder, put in the atmospheric air, it catches fire and burns. This particular property, what you call pyrophoric property. So manganese in the finely powdered state, pyrophoric. The substance which catches fire in the atmospheric air burns. That particular substance what you call pyrophoric nature, the property what we call pyrophoric property. Coming to the next, come to the 8th group. Iron, cobalt, nickel, the 3 vertical columns are kept under single group. Look at here, the 3 vertical columns kept under single group. Why they are kept under single group? The 3 group of elements are having much more horizontal similarity. Look at here, generally we never see an horizontal similarity, but in this iron, cobalt, nickel are similar, and ruthenium, rhodium, palladium are similar, and osmium, iridium, platinum are similar. Osmium, iridium, platinum here. Osmium, iridium, platinum are what are similar. This particular due to much more horizontal similarity. Generally what we observe, a group of elements are similar. But in this case, what you are observing, the horizontal similarity much more. Iron, cobalt, nickel, similar. Ruthenium, rhodium, palladium, similar. And osmium, iridium, platinum, similar. Because of this particular much more horizontal similarity, these elements are kept under single group. This particular group, what you call 8th group, or we call it what? Transition triads. These are also known as what? Transition triads or 8th group. This is about the group-wise study of this particular D block elements, electronic configuration and group-wise study. Now let us see the electronic configurations of these elements. See, consider in the case of this particular scandium, you can take it as what 3D1 and 4s2. This is what 3D2, 4s2. This is what 3D3, 4s2. This 3D5, it is what 4s1, exception chromium. Next manganese, it is what D5 and again S2. In this particular iron, it is simply D6S2. This is what D7S2. This is what D8S2. In the case of copper, you know well, it is D10S1. This is what again D10S2. Let me show the electronic configurations of this 4D also. Then we will have a discussion about this particular abnormalities. Now this you can say it is what 4D1 5s2. This is what 4D2 5s2. This actually we are expecting 3D3, it should be 4D3, but it is not 4D3. Look at here, it is 4D4, it is what 5s1 exception. Molybdenum like chromium, you can take it is 4D5. This is what again 5s1. This is also exception. Coming to this particular technetium, it is like manganese only. Then you can take it is 4D5. Then it is what 5s2. Ruthenium, you see, actually in the case of iron it is D6. It should be also D6, but it is not D6. It is actually 4D7. It is 5s1. See, exception. It is not following the configuration of D6S2, but it is what D7S1. And again rhodium also, it is not D7S2, it is D8S1. Now 4D8 and 5S1. This is exception, this is also exception. Just now I shown to you palladium electronic configuration, it is not D8, it is what 4D10 5S0. It is also exception. Now look at here. In the case of this particular chromium, molybdenum, copper and silver. Silver configuration also what you can take, it is 4D10 5S1. See here, chromium, molybdenum, copper, silver. Their exceptional electronic configurations we can explain based on half-filled stabilities and full-filled stabilities. But see, remaining you see niobium, look at here, niobium, ruthenium, rhodium and palladium. Niobium, ruthenium, rhodium and palladium, they are having what? Abnormal electronic configuration. Still they are not gaining any half-filled orbitals or full-filled orbital. Still they are having abnormal electronic configuration. Therefore, this particular niobium, ruthenium, rhodium, palladium, these abnormal electronic configuration we can explain based on the following factors. We can explain based on following factors. It is due to what? Electron-electron repulsions. It is due to electron-electron repulsions, or it may be due to electron-nucleus attractions. Electron-nucleus attraction. It may be due to shielding effect or screening effect. It is due to shielding effect or screening effect, or it may be due to electron exchange energy force. Electron exchange energy force. So, the abnormal electronic configurations of niobium, ruthenium, rhodium, palladium can be explained based on the following factors. First is what? Electron-electron repulsions, electron-nucleus attractions, and shielding or screening effect, or it may be due to electron exchange energy forces. This is about electronic configurations and group wise study of D block elements. D block element. Next, I will give some questions. What questions are generally appearing in the examination? They are giving different types of ions. They will put a question to you, what number of unpaired electrons are there in the following ions? How to identify the number of unpaired electrons of a given ion in an easy way. I will show how to identify the number of unpaired electrons to identify in a particular given ion in an easy way. Identify the number of unpaired electrons. Identify the number of unpaired electrons in the following ions. Identify the number of unpaired electrons in the following ions. Suppose you are given ion like scandium plus 3, titanium plus 3, scandium plus 3, titanium plus 3, and vanadium plus 3, vanadium plus 3, chromium plus 3, chromium plus 2. Consider manganese plus 4, iron plus 4 or plus 2, take iron, and you consider cobalt plus 4. Let me give some more ions. Let us consider nickel plus 4, and let me say copper plus 2. Such type of ions are given in the examination. They will ask you that what are the number of unpaired electron in the following ions. Whenever a metal ion is given, take first its atomic number. Put the atomic number. You know well, scandium atomic number is what? 21. Put a line in the middle. Then the second number, the second digit, you can take as its electronic configuration. What it is now? D1s2. D1s2 means what? 21 D1s2, 22 D2s2, 23 D3s2, 24 exception, that is what? D5s1. Next 25 D5s2, 26 D6s2, 27 D7s2, 28 D8s2. Once you know the atomic number, you can easily make out the electronic configuration of that particular element. 21 D1s2, 22 D2s2, 23 D3s2, 24, that is exception, D5s1, 26 D6s2, 27 D7s2, 28 D8s2. Like that, you can make the electronic configuration. Once you know the electronic configuration, you can easily make out the number of unpaired electrons in any ion. Many times questions appearing on this electronic configuration, it is more important. Now, scandium 21, then it is given as what? Scandium plus 3. It is losing all the 3 electrons. Therefore, the remaining configuration, 2 electrons lost from S, 1 electron lost from D. Then what is the remaining configuration? D0 and S0. What is the number of unpaired electrons here? 0. Number of unpaired electrons here? 0. Next come to titanium plus 3. What is the atomic number of titanium? 21. 21, it is what? 22. 22 means what? D2s2. How many electrons lost here? 3. 3 means what is remaining? D1 is remaining. D1 is remaining. 2 electrons from S, 1 electron from D. Remaining configuration is what? D1. Therefore, unpaired electrons remaining is what? 1. So, in titanium plus 3, number of unpaired electrons is what? 1. Coming to vanadium plus 3. What is the atomic number of vanadium? Say 23. 23. Put a line, second digit is what? Configuration D3S2. How many electrons lost from here? 3. What is remaining to you? Then it is what? D2. How many unpaired electrons? 2. How many unpaired electrons? 2. Like this, you can easily calculate. Come to the next one, chromium plus 3. Chromium atomic number is what? 24. What is its configuration? But you have to remember this. It is what? Exception. D5S1. How many electrons lost from here? 3. What is remaining? D3 only remaining. D3 means how many unpaired electrons? 3. Next, come to chromium plus 2. We can easily make out the same thing. The configuration of chromium is what? D5S1. 2 electrons last. Then it is remaining what? D4. Unpaired electrons again what? 4. Coming to this particular manganese plus 4. Manganese plus 4. What is the atomic number of manganese? 25. 25 means what you can say? It is 25. Put a line in the middle. Then it will be what? D5S2. How many electrons lost from here? 4. Out of 7, 4 is lost. Then remaining configuration is what? D3. D3 means how many unpaired electrons? 3. So, manganese plus 4 carrying what? How many unpaired electrons? 3. Coming to Fe plus 2. Fe plus 2. Fe plus 2. Atomic number of Fe is what? D6. D6. 26 means D6S2. How many electrons lost? 2. What is remaining here? D6. D6 means how many unpaired electrons? Look at here. 4 unpaired electrons. 1, 2, 3, 4, 5. 5. And 6th electron is what? Paid. How many unpaid? This is what? 4. In D6, the number of unpaired electrons what? 4. Coming to cobalt plus 4. What is the atomic number of cobalt? It is what? 27. It will be D7S2. How many electrons lost? 4. What is remaining? 2 electrons from S, 2 electrons from D. Therefore, the electrons is what? D5 is remaining. D5 remaining one means what? 5 unpaired electron. D5 means it is what? 5 unpaired electrons. 5 unpaired electron. Coming to nickel plus 4. Nickel, what is the atomic number say? 28. 28 means what? D8S2. D8S2. How many electrons lost? 4. So, 2 from S and 2 from D. What is remaining? It is D6. Just now what I said D6 means 4 unpaired electron. D6 means 4 unpaired electron. How? 1, 2, 3, 4, 5. 5 and 6 is what? Paid. Therefore, unpaired electrons are what? 4. This is also carrying 4 unpaired electrons. Coming to this particular copper plus 2. Check it. Copper atomic number 29. But 29 is what? Exception configuration. You know well, even it is there in the very much in 10th class. The chromium and copper electronic configurations are exception. Many times you get these particular 2 points. Very, very important. Then copper is what? 29. It is what? D10S1. How many electrons lost? 2 electrons lost. What is remaining? 1 from S, 1 from D. D9 is remaining. Come on, say D9. How many unpaired electrons? 1 only. 1 only the unpaired electron. Remember, the calculation or identification of number of unpaired electrons is very, very important. In every entrance exam, these questions are appearing. This is the way, in easy way, how to identify the number of unpaired electrons in a given ion. This is the way to identify the in easy way. So, once you know the atomic number, you can easily say its configuration and number of unpaired electrons in a given ion. Which of the following metal? Which of the following metal carry unequal number of unpaired electrons? Unequal number of unpaired electrons in metallic state and in +2 oxidation state. +2 oxidation state. Which of the following metal carry unequal number of unpaired electrons in metallic state and in +2 oxidation state? Answers are, look at here, this Mn, B. Consider nickel, C. Consider copper, D. Let me say chromium. Chromium. What is the question? See, carefully read it. Which of the following metal is carrying unequal number of unpaired electrons? Unequal number of unpaired electron in the metallic state and in +2 oxygen state. Now, consider manganese. Manganese what? 25. 25 means what? D5S2. It is manganese in the metallic state carrying how many? 5 unpaired electrons. Yes, 5. Then you have to see the +2. Come on, make it Mn +2. Mn +2 also carrying what? D5S0. See, D5, 5 unpaired, D5, 5 unpaired. So, in the metallic state, it is carrying 5. In the +2, it is carrying 5. It is not our answer. There should be unequal number of unpaired, but equal number of unpaired, it is not our answer. Coming to nickel. Nickel, you know, D8, 28 means what, you know? D8S2. D8S2, and again you make it. D8S2 means what? D8, how many unpaired electrons? The unpaired electrons in D8 is what? 2. And you are making it nickel again +2. Nickel again +2, still it is carrying what? D8S0. The metallic state D8 only, and nickel +2 also D8. Then both of these same number of unpaired electrons, here 2, here also 2. This is not our answer. There should not be equal number. There should be unequal number of unpaired electrons. So, A bit is not the answer, B is not the answer. Let us check it. Copper. Copper atomic number is 29. The electronic configuration coming to be D10S1. The metallic state, how many unpaired electrons it is carrying? Only 1 S1. It is carrying 1 electron. Coming to this particular copper +2. Copper +2 electronic configuration is what? D9. D9, how many unpaired electrons again? 1. So, copper in the metallic state, 1 unpaired electron. In +2 also, 1 unpaired electron. Therefore, it is not our answer. Equal. So, this is carrying equal number of unpaired. It is also carrying equal number of unpaired. Third bit also carrying an equal number of unpaired. These are not the answer. Coming to chromium. Chromium is what? 24. Many times you know this is this copper. Chromium is carrying what? The abnormal electronic configuration D5S1. How many unpaired electrons in metallic state? 6. 5 plus 1, 6. Now, you say this particular chromium +2 electronic configuration you take, this will be what? D5, no, it is +2 means D4S0, D4S0. So, chromium in the metallic state, 6 unpaired electron, chromium in the +2 state, 4 unpaired electrons. So, this is actually correct answer. The metal which is carrying unequal number of unpaired electrons in the metallic state and in +2 oxygen state, this is what D the answer. So, like this question it is little typical, but we have to think and answer. So, among all these, chromium is carrying unequal number of unpaired electrons in the metallic state and again in +2 oxidation state. Next, this type of questions are appearing in the different entrance exams. These are some of the questions which are appeared in the recent entrance exams. Let us enter into properties of D block elements. Properties of D block elements. D block elements. Let us say first one, reactivity. Reactivity. Second, let me say metallic property. Third one, densities. Densities. Let us discuss first all this. Reactivity. The reactivity of D block elements is less in comparison to S block elements. Reactivity of D block elements is less in comparison to S block elements. Why they are less reactive? What are the reasons? This question is appeared and repeating many times in the different entrance exams. First one, why the D block elements are less reactive? First one, it may be due to high sublimation energies. It may be due to high sublimation energies or high melting point. It is due to high sublimation energies or high melting point. Consider any S block element. S block element on heating, they are easily convertible into what? Vapor. They are easily sublimable and their melting points also less. Therefore, once D block elements, their sublimation energies are less and their melting points are less, therefore they are actually more reactive. But in the case of D block, you take any iron metal like that. Is it easily sublimable? No. Their melting points and sublimation energies are very high, therefore D block elements are less reactive. First one. Next, they are having high IP values. High IP values. So, S block elements that bigger in atomic size, their IP values are less. They easily lose electrons, enter into chemical reactions. But in the case of D block, their IP values are high. They cannot easily lose the electrons. Therefore, they cannot easily enter into chemical reactions. Therefore, they are less reactive. Coming to third one, their heat of hydration values are less. Heat of hydration values are less. Now, you take first A group of metals, put into water. Put into water. As you are putting into water, then many water molecules are occupying the particular ion, large amount of heat is liberated. Therefore, they are more reactive. But you take a iron piece, put into water. What happens? Nothing happens. After a few days, it may be getting rusted, but it is not reacting freely with the water as the S block elements are reacting. So, D block elements are less reactive due to these particular reasons. First one is high sublimation energy, high melting points, low. This is what high IP values, and again third one, low heat of addition. Due to these three reasons, D block elements are less reactive than S block elements. Coming to metallic property. Metallic property. Now, D block elements are less metallic. D block elements are less metallic than S block elements. Why less metallic? What is actually metallic property? The tendency to lose electrons, we call it as what? The metallic property. So, come on, consider among D and S block element which are having greater tendency to lose electrons. Yes, S block elements are bigger in size, their IP values are less, therefore, they are having greater tendency to lose electron. Therefore, S block metals are highly metallic, but D block elements are less metallic. So, what I said here, D block elements are less metallic than S block element. What you can easily make a relationship, metallic property inverse to IP. Metallic property inverse to IP. Greater the IP, less the metallic property. Next, densities. Next, densities. Let us consider third B group 2. Third B group 2, consider either 8th group or up to first B group. 8th group 2, this third B group 2, 8th group or up to first B group, the densities are gradually increasing. Consider in the case of second B group. Second B group means what you can take? Simply consider zinc. Zinc. In the case of zinc, it is actually fully filled d orbitals. Fully filled d orbitals means what? D10S2. Fully filled d orbitals and s orbital. Once any atom is having fully filled valence shell, there will be inter-electron repulsions. Electron charge cloud is expanding. Atomic size is increasing. Density will be decreasing. Therefore, in comparison to copper, this particular zinc is little bigger in size. Once copper to zinc, atomic size increasing, density will be less. What I said, third B group to 8th group or up to first B group, densities are increasing. In the case of second B group, due to fulfilled orbitals, inter-electron repulsions, electron charge cloud is expanding. Electron charge cloud is expanding. Atomic size is increasing, density is decreasing. Density is decreasing. Coming to the next point, 3D, 4D and 5D you take. 3D to 4D, 4D to 5. 3D to 4D, the density has to increase. Yes, increasing. Density is increasing. But 4D to 5D, density is becoming almost double. Density is becoming almost double. Are you looking here? 3D to 4D, density has to increase. Yes, increasing. But 4D to 5D, that density has to actually normally increase. But here, not normally increasing. This 4D to 5D, density is almost becoming double. This is due to what you can say lanthanide contraction effect. 3D to 4D, normal increase. 4D to 5D, abnormally becoming double. This is due to lanthanide contraction effect. Lanthanide contraction effect. Next, among all the D block elements, remember iridium is having what? Highest density. Iridium is having highest density. Second element coming to be osmium. Second is osmium, and scandium is having lowest density. Scandium is having lowest density. Once again I am repeating, among all the D block, iridium is having highest density, second is coming to be osmium, lowest density among the D block is what? Scandium. This is about reactivity, metallic property and densities. Next let me talk about atomic radii and IP values of D block elements. Atomic radii. Atomic radii, let me discuss first again here. Now, the atomic radii left to right gradually decreasing. Left to right in a period, the atomic radii is gradually decreasing. Similarly, the case here, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zincutic. Here, scandium, titanium, next up to zincutic, the atomic radii are gradually decreasing up to nickel. Scandium to nickel, the atomic radii are gradually decreasing. But in the case of copper and zinc, what is the electronic configuration of copper? D10S1, this is what D10S2. In the case of copper and zinc, we are clearly observing this fulfilled orbitals. One is fulfilled orbitals are there, they have inter-electron repulsions. Electron charge cloud is expanding. Imagine this particular nickel is this much big, but because in the case of copper, due to fulfilled orbital, inter-electron repulsions, electron charge cloud is expanding. Therefore, nickel to copper increasing. In the case of zinc also, it is fulfilled d orbitals and again inter-electron repulsions. Therefore, nickel to copper atomic size increasing and copper to zinc also atomic size increasing. So, scandium to nickel atomic size are decreasing. In the case of copper and zinc, due to fulfilled orbitals, inter-electron repulsions, electron charge cloud is expanding. Therefore, nickel to copper, copper to zinc atomic size are increasing. Next, look at here. Now, let me say the second point. Here, chromium to nickel atomic size are more or less same. Chromium to manganese, manganese to iron, iron to cobalt, cobalt to nickel. Atomic size difference is very little, though these are having more or less identical atomic sizes, we can say. This is due to two reasons, we can say. It is due to either you say shielding effect or you say screening effect. It is due to shielding effect or it may be due to screening effect. Shielding or screening effect. Second point, what we can say here, it is due to entry of differentiating electrons into d orbitals of the penultimate shell. The differentiating electron entering into d orbitals of the penultimate shell. Due to these two reasons, chromium to nickel, the atomic size are found to be more or less identical. Next, consider here 3D series to 4D series, 4D series to 5D series to take. 3D to 4D atomic size has to increase. Yes, increasing. 3D to 4D atomic size is increasing. But 4D to 5D atomic size has to increase, but not increasing. It is decreasing or remaining more or less same. Look at here that 3D to 4D you are observing a increase, but 4D to 5D the atomic size are remaining more or less same. This is due to what reason? Lambda-wide contraction. It is due to Lambda-wide contraction. The 4D and 5D elements are having more or less same sizes. Next, see in the periodic table, if you consider any two elements you take X and Y. If the X and Y are having more or less identical atomic sizes, the remaining properties are all found to be more or less same. The X and Y elements are having more or less same atomic size, their properties are found to be more or less same remaining properties. But whenever there is a large difference in the atomic size between X and Y, they are showing remaining all other properties much more differences. Therefore, what you are observing here, 3D to 4D size difference is much. Therefore, 3D and 4D elements are showing much more dissimilarities, much more differences in their properties. But what you are looking here, 4D and 5D due to Lambda-wide contraction effect, 4D and 5D are having more or less same sizes. Once they are having more or less same sizes, we can consider that 4D and 5D are showing much more similarities in their properties. What we can conclude now? 3D to 4D atomic site difference is much. Therefore, 3D and 4D elements are exhibiting greater differences in their properties. Due to Lambton and contraction effect, 4D and 5D are having more or less same sizes. Once atomic sizes are same, their properties are found to be more or less similar. So, 4D and 5D are similar in their properties, and 3D and 4D are showing much more dissimilarities in their properties. This we can understand from atomic radii of this particular 3D, 4D and 5D series of elements. Now, you talk about this is very important again, the decreasing order of the atomic size of 3D series of elements. I am putting on the board, check it. Scandium is bigger than titanium. Titanium is bigger than zinc. Look at here, the zinc should be smaller. According to general trend in the periodic table, periodicity, zinc should be smaller. But where I written the third element I am writing. Why I am writing that one? Fulfilled orbitals, inter-electron repulsions, and electron charge density is what? Expanding. Therefore, zinc is actually bigger in size. So, scandium is bigger than titanium, titanium is bigger than zinc. After zinc, you get this particular vanadium. After vanadium, look at here, copper you are getting. So, scandium is bigger than titanium, titanium is bigger than zinc, zinc is bigger than vanadium, vanadium is bigger than copper, remaining is common trend chromium, manganese, iron, cobalt, nickel. This is what order of decreasing order of atomic size of 3D series of elements. Try to remember entire series so that they are in the examination they give only 4 or 5 elements, and they will ask you arrange in the increasing order or decreasing. Once you remember entire series only, you can easily make out how the decreasing and the increasing order of or the given number of elements. Then we discuss next IP values of D block elements. IP values of D block elements. IP values of D block elements. Now, left to right, the first and second IP values, first and second IP values. The first and second IP values from left to right as a general trend in the periodic table, the 3D series, the first and second IP values gradually increasing. But in the case of consider chromium and manganese. Take chromium and manganese. What is the electronic configuration of chromium? You know well, D5S1, and manganese it is what D5S2. Chromium is what? D5S1, and manganese is what? D5S2. Now let us take from which you can easily remove the electron. Can you say? Now the removal of electron from S1 is easy, but S2 is difficult. Therefore, I write a statement. Look the board. The first IP of manganese is greater than first IP of chromium. First IP of manganese is greater than the first IP of manganese. First IP of manganese is greater than first IP of chromium. Come to next point. Once I remove an electron from this, chromium plus 1. Then I remove an electron from this, then it will be manganese plus 1. Now look at the board. This chromium plus 1 is having D5 configuration, but manganese plus 1 is having D5S1 configuration. Now check it. The removal of first electron from manganese is difficult. Therefore, I written first IP of manganese is greater than first IP of chromium. Next, after the removal of one electron from manganese and chromium, manganese is having D5S1, chromium is having D5S0. So that the removal of second electron from chromium is difficult, but you can easily remove electron from S1. The same statement I write like this. Look the board. Second IP of manganese is less than second IP of chromium. Second IP of manganese is less than second IP of chromium, but first IP of manganese is greater than first IP of chromium. The same discussion holds good for copper and zinc pair also. Same discussion we can say for copper and zinc. The first IP of zinc is more, but second IP of zinc is less. So, same whatever the discussion we are discussing for this particular chromium and manganese, same discussion holds good for the pair copper and zinc. Next, consider 3D series to 4D series, 4D series to 5D series. 3D series to 4D series IP values have to decrease. Yes, decreasing. But 4D series to 5D series IP values have to decrease, but not decreasing the IP values 4D series to 5D series showing an increase. 3D to 4D IP values decreasing, but 4D to 5D IP values showing a increase. This is due to again consider well lanthanide contraction effect. 3D to 4D IP values decreasing, but 4D to 5D IP values increasing. This is due to lanthanide contraction effect. Next, among all the metals, remember it's very important, among all the metals mercury is having highest first IP. Remember, among all the metals in the periodic table, mercury is having highest first IP, This is about IP values of this particular D block elements. Melting points and boiling points. The D block elements are having greater melting points and boiling points in comparison to S block elements. Why D block elements are having greater melting and boiling points in comparison to S block? It is due to formation of two types of bonds. One is metallic bonds. By involving of ns orbital electrons. Next, B. It is due to formation of covalent bonds. These covalent bonds is due to involving of n-1 d orbital electrons. So, one is metallic bonds, second one is covalent bonds. These two types of bonds are there in between the metallic atoms. To break this particular two types of bonds, they requiring more amount of energy. Therefore, the D block elements are having greater melting point and boiling points in comparison to S block elements. Next, the D block element which is having greater number of unpaired electrons in d orbitals. The D block element which is having greater number of unpaired electrons in d orbital, that is capable of forming more number of covalent bonds. Once it is capable of forming more number of covalent bonds, that is having greater melting and boiling point. So, what we can conclude? The D block element which is carrying more number of unpaired electrons in d orbital, that is capable of forming more number of covalent bonds, and that is having greater melting and boiling point. Therefore, we can show that the third B group to sixth B group, the number of unpaired electrons are gradually increasing, the melting and boiling points also gradually increase. Let me show this. Now, you consider in the case of third B group, third B, fourth B, fifth B and sixth B group, fifth B and sixth B group we take. Now, we consider here 3D series and 4D series and 5D series we take. Here it is at scandium, titanium and vanadium and chromium. Scandium, titanium, vanadium and chromium. Similarly, you can take yttrium, zirconium, niobium and molybdenum. Then you can take lanthanum, hafnium, tantalum and tungsten. So, here what is the configuration of this particular D1 to D2 to D3, chromium configuration, what D5. This is the electronic configuration. What I said, the element which is carrying more number of unpaired electrons, that is capable of forming more number of covalent bond, that will be having greater melting and boiling point. Therefore, third B group to sixth B group, number of unpaired electrons in d orbitals increasing, that is capable of forming more number of covalent bonds, and melting and boiling points gradually increase. Therefore, in the 3D series, highest melting point we have to see for chromium, but surprisingly it is not seen in the chromium. This vanadium is exhibiting highest melting point among 3D. Why? This melting point and boiling points not only dependent on the number of unpaired electrons, also dependent on the nature of the metallic lattice. Therefore, vanadium is having what? Typical metallic lattice. Therefore, vanadium, because of typical metallic lattice, it is having highest melting point among the 3D series of elements. Coming to 4D and 5D, normal trend only observed. In the case of this particular 4D, this molybdenum is having highest, and in the case of 5D, this particular tungsten is having highest. I already mentioned to you this particular among all the D block, or among all the metals, would say among all the metals, tungsten is having what? Highest melting point, and lowest melting point what? Mercury. Highest is tungsten and lowest is mercury. Among the 3D, highest is vanadium. Among the 4D, highest is molybdenum. Among the 5D, tungsten. Moreover, tungsten is having what? Highest melting point among all the metals. The order of melting points trend, if you want to write, look at here. Then scandium is less than. Scandium melting point is less than titanium. Titanium is less than vanadium. Vanadium is greater than chromium. Chromium is greater than manganese. Manganese less than iron, and iron is more than cobalt and nickel and copper and zinc. This is the trend of this particular melting point. But you have to remember only 4 is very important. Vanadium is having greater than chromium. Chromium is having greater than iron. Iron is having greater than manganese. These 4 elements, you remember the order of melting points. Next, the copper and zinc are having generally low melting points. It is due to what reason? In the case of copper and zinc, it is D10 electronic configurations are there. Once they are having what? Fulfilled d orbitals, D10 electronic configurations, they cannot form any covalent bonds. Copper and zinc, the covalent bonding is not possible. Therefore, they are forming only one type of bonds. Therefore, their melting and boiling points are comparatively less. Melting and boiling points are comparatively less. This is about the melting and boiling points of D block elements. Oxidation states. See, most of the D block elements exhibit variable oxidation states. Most of the D block elements exhibit variable oxidation states. Why they exhibit variable oxidation states? It may be due to energy difference between Ns and N-1 d orbitals is less. Energy difference between Ns and N-1 d orbitals is less. What is happening by that? The electrons from s orbitals, electrons from d orbital easily involving in bonding. Therefore, they are exhibiting variable oxidation states. Next, it may be due to presence of unpaired electrons in d orbitals. It may be due to presence of unpaired electrons in d orbitals, incompletely filled d orbital. This is also one of the reasons why they exhibit this variable oxidation states. It may be due to presence of unpaired electrons and incompletely filled d orbitals. Next, third point, you see the energy difference between successive IP values. Energy difference between successive IP values is less. Energy difference between successive IP values is less. What is this successive IP values? Means the first IP, second IP, third IP, fourth IP you take. The first IP to second IP, second IP to third IP, third IP to fourth IP. The energy difference between the IP values is less. Therefore, by supplying little more amount of energy, suppose first electron removal is requiring 100 kilocalories of energy. For example, I am giving. This is requiring only 120, 130, 140 like that. By supplying little amount of energy, we can remove successively the electrons. Therefore, once the energy difference between the successive IP values is less, therefore, because of this reason they are exhibiting variable oxidation states. First reason is energy difference between ns and n minus 1 d orbitals is less, presence of unpaired electrons, incompletely filled d orbitals, and energy difference between successive IP values is less. Therefore, they are exhibiting variable oxidation state. Now, let me show in each series, 3D series, 4D series, 5D series, what is the common oxidation number, what is the minimum oxidation number, what is the maximum oxidation number. Series, common oxidation number, common oxidation state, minimum oxidation state, maximum oxidation state. Series, common oxidation state, minimum oxidation state, and maximum oxidation state. Let us take first 3D series. 3D series. See, common oxidation state is what? +2. Minimum oxidation state is what? +1. See, minimum oxidation state in 3D series generally exhibited by what element? Which element? It is, you can take copper +1 and chromium also, now and then exhibiting +1 oxidation state. This is what? +1 copper and chromium. Maximum oxidation state, this 3D series, this is what? Manganese. Manganese exhibiting maximum +1. Maximum +1. In what compound is exhibiting? You can consider KMnO4 or you can consider MnO3F. MnO3F. Though KMnO4 and MnO3F, manganese exhibiting what? Maximum oxidation state. So, common and minimum and maximum oxidation state. Coming to 4D series, we take 4D series. Common oxidation state again +2 and minimum oxidation state exhibiting +1. +1 is exhibited by what? This you take molybdenum, you take molybdenum +1 and again silver also exhibiting +1. So, minimum +1 molybdenum and silver, and maximum oxidation state is +8. This is generally exhibited by ruthenium in ruthenium tetroxide. Ruthenium tetroxide, ruthenium is exhibiting +8. Again in 4D, common, minimum and maximum. You can take 5D series. 5D series is what? Common oxidation state, minimum oxidation state is actually +1. This is generally exhibited by Rm Au +1 is the. Then maximum oxidation state +8 in 5D. This is what in osmium tetroxide. So, osmium in osmium tetroxide exhibiting +8, common oxidation state, minimum oxidation state, maximum oxidation state in each series 3D, 4D and 5D. Now, and then we talk about stable oxidation state. What are stable oxidation states? What are stable oxidation states? Whenever a metal ion is gaining either D0 electronic configuration or stable D5 electronic configuration or stable D10 electronic configuration, either D0 or D5 or D10 electronic configuration, such oxidation states are considered to be stable oxidation. So, the metal ion in which oxidation state gaining either D0 or D5 or D10, such oxidation state is found to be more stable oxidation state. Consider scandium +3, yes, D0, titanium +4, also D0. These two oxidation states are stable for scandium and titanium. And you can take chromium +1 you take and manganese +2 you take, these particular two, and you can also consider iron +3. In these three oxidation states, these metal ions are having stable D5 configuration. Therefore, stable oxidation state we can consider. D10 come on, say now copper +1 you take and zinc +2. Copper +1 and zinc +2. All these oxidation states we are considering as stable oxidation states. Why you consider as stable oxidation state? Because in these particular oxidation states, the metal ions are gaining either stable D0 or D5 or D10 electronic configuration. Therefore, these are considered what stable oxidation state. Next, you are given a compound like MnO you take, Mn2O3, MnO3, MnO, Mn2O3, MnO3. What is the oxidation number of this? Plus 2. What is the oxidation number of this? Plus 3. What is the oxidation number of this? Plus 6. This is what? Plus 2, plus 3, plus 6. Same metal ion, but different compounds, different oxidation state. Wherever minimum oxidation state is there, minimum. And this is what? Medium oxidation state. This is what? Maximum. Medium oxidation state and maximum oxidation state. So same metal ion we are looking, but in one of it is minimum, the medium, and again maximum. Wherever the metal ion is exhibiting minimum oxidation state, that is found to be more ionic, or you can consider basic. Ionic or basic. Wherever maximum it is exhibiting, then you can consider this is highly covalent, or you can consider highly acidic. Wherever it is the medium oxidation state is there, consider this will be what? Amphoteric. Both the properties are exhibiting amphoteric behavior. So once you see the compounds and their oxidation number, you can easily identify which is more covalent or which is more acidic, which is more ionic, and which is more basic. You can easily understand. Based on this, minimum is basic, maximum is what? Acidic, medium you can consider what? Amphoteric. How the question appear in the examination, how to answer it. Which of the following is highly acidic oxide? Highly acidic you say of. Highly acidic. Which of the following is highly acidic? See, VCl2, VCl3, VCl4, and you are given VOCl3. VCl2, VCl3, VCl4, and VOCl3. But the oxidation number here, what do you want actually? Acidic. Acidic means what I said to you, it should exhibit greater, highest oxidation state. Here plus 2 oxidation state, here plus 3 oxidation state, here you take plus 2, here you take plus 3, here you take plus 4, but it is exhibiting what? Plus 5. So highest oxidation state, therefore it is what? Highly acidic compound. Like this, based on the given compounds, you have to see which is having lower oxidation state, which is having higher oxidation state. Accordingly, you can easily decide which compound is more acidic or more basic. Easy concept to identify the nature of a given compound.